Okay, today we're going to cover Chapter 8, Sections 4 through 5, and we're going to go over concept questions 5, 6, and 9, and exercises 18, 24, 30, and 61. Again, I remind you how important it is for you to try and struggle with these problems on your own before looking at my hints and solutions throughout this video. So go ahead and start with concept question 5. Go ahead and take a look at concept question 5. Okay, so we have two balls in circular motion. One is going through a radius that's twice as large as the other. And the question says, what is the tension in the string of these balls as they're going around the circle if the tangential velocities are the same between the two? How do the tensions relate? And so what's the main idea here? How is tension related to speed? Okay, so Newton's second law says that F net equals ma. Okay, and when we have this ball flying around in a circle, it's attached to a string, the only force acting is the tension, and it's pointed in the radial direction, radially inward, which means that the acceleration is radially inward, and that's a centripetal or radial acceleration, which has its special relationship of mvt squared over r, the radius of the circle. Okay, so if the tangential speed is the same in the two cases, then how do the tensions relate? So since tension is inversely related to the radius of the circle, that means the circle with the larger radius has a smaller tension. Okay, so that's assuming that the tangential speed is the same. Well, in part B, it says, well, what if instead we hold the angular speed constant? How would we adjust this to relate tension to angular speed? So this problem is reminding us of how tangential speed and angular speed are related, and it is by the radius. Tangential speed is equal to the radius times the angular speed. So we can just replace tangential speed with r omega, square both things. We'll have two factors of r up top, one of them canceled by this factor of r below, and we end up with an mr omega squared. So now, if you hold the angular speed constant, well, now the tension is directly proportional to the radius. And so the one with the larger radius will have a larger tension. Okay, move on to number 6. Check out 6. Okay, so a hint here for the comments that Ramon and Sally are saying is that they both are saying something correct, but they both use one word incorrectly, and that word is net. Okay, with that hint, see if you can answer this question. Okay, the idea is that if they took out that word net, they both would be correct. They both say that there must be a net force in one of the two directions, either tangential or radial. But if they just said there is a force in the tangential direction and a force in the radial direction, they'd both be correct. Because if a car is speeding up around a circular track, then it must have a tangential acceleration. It's speeding up, which means that there is a force tangential. Okay, and so here's that car traveling in a circle. It must be speeding up, so that's a tangential, which means there is a tangential force. But it's also going in a circle, which means there's a radial acceleration, which means there's a radial force. The net force would be in the direction of the net acceleration, which would be the vector sum of these. This would be a net, and the net force would be in that direction. So the important thing here is that there are components, one tangential and one radial. Okay, let's move on to number 9. Go ahead and take a look at number 9. Okay, this problem emphasizes what we just discussed in number 6, and it emphasizes the importance of looking at how the forces relate to the accelerations. This one focuses mostly on the radial acceleration. Okay, and this idea is going to set this theme for the rest of the reading, the rest of this class activities. Okay, so we have a ball flying around this circle, and at the top, if you swing it too slowly, the string will go slack, and the ball will not make it over. It'll end up being in projectile motion and just kind of fall down. And the question is why? What's going on there? Okay, explain why there's a minimum speed to keep the ball moving in a circle. Okay, so if it's moving in a circle, what is the direction of the acceleration? The answer is, at this point, it's radially inward, and so that is down. Okay, so at the top of this vertical circle, radially inward means down. Okay, and if I look at that and draw a free body diagram, well, I know gravity's pulling down on it. Okay, and there's also a string pulling down on it. Okay, so I have a tension there. All right. And because I know the acceleration is down, I know that the net force in that component must be down. All right. And the net force by Newton's second law is equal to what? It is equal to MAR for this component. But MAR is equal to MV tangential squared over the radius by that super important relationship. And so if VT gets small, what happens to F net? Well, F net gets small. Okay? But F net is equal to T plus mg. So we have T plus mg here. Can mg get small? It can't. I mean, it's mass times gravitational acceleration. I can't change that. The only thing that can get small is the tension. And so if this gets smaller and smaller and smaller, that means the tension must be getting smaller and smaller and smaller. And if this gets to some point where the tension goes to 0, then the string has no tension and it would go slack. Okay, meaning that the string would crumple up. All right, and that's the case where this reaches that critical speed in which this is barely making it in circular motion. And if you go any slower, this equation can't work anymore because now the acceleration is not circular motion, it's not centripetal acceleration, it's just projectile motion, and we just have a downward force of gravity that's everywhere acting and just follows a projectile path, a parabolic path instead of a circular path. Okay, so this net force related tension to this speed because we were able to see that the acceleration points downward, and therefore how the tension related to the force of gravity. This idea, this process is going to be super important. We're going to see it applied in nearly every of the remaining problems. Okay, so we recognize the direction of the acceleration, we apply it to a free body diagram and recognize how that affects some applied force relative to the force of gravity, and it's related to a speed. Okay? All right, so let's move on to our exercises. Look at exercise 18. Take a look at that one. Okay, so here we have a car driving over a hill. And if the car drives too fast, it'll jump the hill. It'll leave the hill. Okay? If it drives slow enough, it'll follow the circular curvature of the hill, so it'll follow the circular motion. So as your hint, apply what you just did in this concept question here to this problem. What's the direction of the acceleration? What does the free body diagram look like? What's the direction of the net force? What's it related to? And then try and find if you can understand how to find a maximum speed. Okay, so your acceleration is downward because the car is driving over the circular loop. It's at the top, and so it's the radially inward is down at that point. Its free body diagram looks similar. It's got a downward force of gravity, but it's got a normal force pushing up. How big is that normal force? Okay, how long do I draw that? it should be shorter than the force of gravity because the acceleration is pointing down, which means the net force must be pointing down. And therefore, the force of gravity must be bigger than the normal force. Okay. Now, if I set that equal to m, I'm just going to jump to vt squared over r. Okay, that's my radial acceleration because this is the radial force, net force. But what is it? Well, choosing down to be positive, I'm going to have mg minus n equals mvt squared over r. So if this is getting big, if I drive faster and faster and faster, what happens over here? Okay, mg can't change, which means if this is getting bigger, this side has to get bigger, which the only way that can happen is if the normal force gets smaller and smaller and smaller, which makes sense because if I go too fast, I'm going to jump this hill. That means I'm not going to be in contact and my normal force will go to 0. And that is that critical condition. This gets bigger and bigger and bigger until it reaches V max, which is when this got smaller and smaller and smaller until it reached 0. And so by doing that, we get mg equals mvt squared over r, and we can solve for that vt. If you do, you'll get 22 meters per second. All right, so recognize the process. We just did it again. Noted the direction of our acceleration, allowed us to determine the direction of net force and therefore the relative size of forces related to our tangential speed, and then used our Newton's second law to try and solve for a critical value. Okay, let's move on to 24. Okay, what does 24 look like? Okay, so for 24, we have a ball swinging in a vertical circle. So it's very much like this one, only now we're at the bottom of the circle and we're given the tension. Okay, so draw a picture and a free body diagram and try and apply that process. Okay, so if I'm at the bottom of my swing here, then the acceleration is upward. The radial acceleration is upward. Okay, if I look at that, I have a downward force of gravity, and I have an upward force of tension, and how long should it be? Well, I know with that upward acceleration, I should have an upward net force, which means my tension should be bigger than my force of gravity in order to achieve that. And then this equals what? Mass times the tangential speed squared over the radius. Again, that's AR is equal to VT squared over R. And now in this case, I'm choosing up to be positive. I put a plus sign over here. So up is positive, which means tension minus mg equals mvt squared over r. Okay. Now from this, we can now solve for the speed. We know the tension. We know the mass. We know the radius. We can solve for vt. And in doing so, we'll find vt equals 5.5 meters per second. So again, that same process, we've now done it 3 times. We know the direction of our acceleration because of the circular motion. It tells us the direction of the net force in that component. Okay, and then we have, now I need to be careful when I say net force. In these cases, we've assumed no speeding up or slowing down. And so this would be true net force in that component, okay, even if it was speeding up or slowing down. But we've applied, so we know the direction of that radial component of acceleration, tells us the direction of the net force in that component, allows us to infer a size of a force relative to the force of gravity. We can relate that to tangential speed and then find critical values or just other values. Okay, let's move on to 30. Go ahead and take a look at 30. Okay, this problem seems really complex. Now it's asking for a tangential acceleration to brake. But if we remember one thing, it will help make a connection to everything we've just done. Okay? And that is that the frictional force that would slow the car down is related to the normal force. If the car is braking, then it is skidding, and so there's a rubbing or a relative motion between the road and the car, and that would be a kinetic frictional force. Okay, and that is equal to mu k times the normal force. Okay, so mu k times the normal force. But the normal force is related to everything we've just done here. So the frictional force allows us to find a tangential acceleration, but it's the normal force that allows us to find this. So with that clue, with this connecting piece, see if you can finish solving the problem. Okay, to help, let's draw that picture. We have a car traveling on a straight piece of road, a car traveling at the bottom of a valley, a circular valley, and a car traveling at the top of a circular hill. And that valley and hill have the same radius of curvature. Okay? So our goal is to find the braking acceleration or the tangential acceleration, which in order to do that we need to find the braking force, which is the frictional force. But in order to do that, we need to find the normal force. So the bulk of this problem is to find the normal force. Okay? So, in this case, what is the direction of the radial acceleration or the direction changing acceleration, which is the perpendicular to the motion? So in this case, it's traveling straight. It's not changing direction. So A sub r is 0. Okay? What is the direction of A sub r, or the radial acceleration in this case? It is up. What is the direction of the radial acceleration in this case? It is down. Okay, this is at the bottom of a circle, so the center of the circle is above. This is at the top of a circle, so the center of the circle is below. Okay. Now, in each of those cases, draw the radial component of the free body diagram. Okay, in this case, my car is here, force of gravity down, Fg, and there's no net force in the radial direction, so that means my normal force is equal, or equal size. Over here, force of gravity doesn't change. It's the same size as previously. But what is the direction of the net force? It is up, which means the normal force must be bigger than the gravitational force. Okay, and over here, gravitational force is no different, but the net force is down, and therefore the normal force must be smaller. Okay, and I'm going to be careful here and put R and R. It's the net force in that component. Okay, and I guess I also need to be careful here and finish off my vectors. But the important thing is that the normal force is equal to mg in this case, the normal force is greater than mg in this case, and the normal force is less than mg in this case. And so we'll need to find that out. Okay, see if you can now apply that, translating your diagrams to a Newton's second law, like in these cases, and see if you can continue to solve this problem. Okay, so I'm going to add my frictional forces here. Okay, my kinetic frictional force. This one's going to be bigger because I could see that the normal force is bigger. This one's going to be smaller because I can see that the normal force is smaller. So using my Newton's second law in the radial directions, okay, choosing the direction of acceleration to be positive. In this case, it's 0, so I'll just choose n minus mg equals 0 or n equals mg. In this case, I'll choose up to be positive, which means n minus mg equals mv squared over r. Okay, and that is my tangential speed, which means n is equal to mg plus vt squared over r. So it is bigger. See, it's bigger than mg. And over here, I'm going to choose down to be positive because that's my acceleration. So I'm going to say mg minus n equals mv squared over r. Okay. And solving for that n again, n equals mg minus vt squared over r. And see, n is smaller. And now the last thing to do is just to say, okay, well, in the tangential component, my net force, F net tangential, is equal to ma tangential. All right, but F net tangential is just Fk, and Fk is just mu k times n. So At, the tangential component, is then equal to mu k n divided by m. All right. And I'll let you plug in the numbers. This mu k, we can look that up. That is for a car driving on a road. That is 0.0 or 0.8 is a kinetic frictional force. That's from chapter 6. There's a table for rubber on concrete. Okay. And if you look that up, in the first case, you'll get something that's just a little bit smaller than mg because n equals mg. And so the m's cancel. You get 0.8 times g. In the second case, you'll get something a little bit bigger because the m's still cancel, and so your g becomes a little bit bigger, but then you multiply by 0.8. And in the final case, it's a little bit smaller than the first case. So I'll let you plug in your numbers to figure that one out. Okay, so now, as we proceed to this last problem, it's a pretty complicated problem, but I want you to focus on this process. Okay, this was pretty complicated, but the bulk of it was recognizing how do we calculate the normal force. And from that, we can go back and find frictional force. Okay. This last one, we're going to do some kinematics and stuff like that as well. We need to recognize just how are we using our knowledge of the circular motion. Okay, so let's go ahead and pause and go look at problem 61 and see how much of it you can do.